Hello and welcome to tutorial 8 of the advanced ANSYS tutorial series on EGA324. This tutorial will be based upon the development of 2D FLUENT models to simulate the boundary layer flow over a flat plate. In particular, this model is based upon an original tutorial you can find on the cornell.edu website, as you can see in the tutorials course notes. However, we take this a step further. We will be modeling both laminar and turbulent flow, and the geometry has been adapted to match the geometry of the experiment E2, the boundary layer experiment, which we'll be undertaking in the second 2 weeks of term. This tutorial builds upon the previous tutorials in the intermediate course, particularly in using ANSYS FLUENT with the turbulent flow model. So in addition to what you've learned so far, you will continue to create geometries and surfaces with sketches in Design Modeler. You'll mesh your model in the desktop meshing tool. You'll work with FLUENT to select a turbulence model and modify properties, apply boundary conditions, and run the actual FLUENT analysis. We will do the post-processing of the FLUENT analysis in CFD Post, part of the desktop, ANSYS desktop suite, and we'll look at vector plots and contour plots. We'll also use a technique of creating variables so that we can create a variable called normalized velocity and export that data to Excel for later comparison with the empirical boundary layer thicknesses and for you to be able to compare your experimental data to. Let's start with the specifications. Well, this is going to match the experiment, the boundary layer, which consists of the test section in the AF100 wind tunnel, the College of Engineering. It's labeled experiment E2. On this, you've got a flat plate, which is aligned halfway up the test section. So your distance D is about 150 millimeters. The height of the test section, as you know by now, is 0.3 meters. The length of the test section is 0.6 meters, and the width of the test section is 0.3 meters. Okay, and the plate stretches from one side to the other. Arranged on the plate are 1, 2, 3, 4, and 5 short foils, 10 millimeter foils. And at the on the leading edge of these foils are a series of taps. So we've labeled these as tap at 40 mil, tap at 90 mil, tap at 150 mil, tap at 220 mil, and tap at 300 mil. Each of these foils has 5 tap locations arranged over a distance of about 10 millimeters up the tap. And that domain of the test section, namely, we're going to do a 2D model, which is 0.6 meters long and 0.15, 150 millimeters tall. So we are going to develop the flow models to simulate the experiment, and we're going to look at the growth of the boundary layer, as you can see here, and see how this compares to the empirical models, which are such as Blasius for the laminar and the turbulent boundary layer thicknesses. In the experiment, you'll be looking at various velocities, somewhere between 10 and 30 meters per second, 3 specifically, and we're going to be able to change those velocities as part of the model so you can compare them. The definition of the boundary layer thickness is that the point at which the velocity reaches 99% of the free stream velocity is the point at which the boundary layer is defined at. For all flows over a body, we have a period in which there is a laminar boundary layer, then there's a transition through to a turbulent boundary layer, always keeping in mind that there is always a small viscous sublayer which remains after the boundary layer has developed. The Reynolds number, when talking about boundary layer, is dependent upon the x position from some initial point of the plate. So that the Reynolds number is Rex equals density rho times the velocity times the position x along the plate divided by the viscosity. Okay, so if you work out for the and taking care to make sure that your dimensions are in SI units, therefore in meters. So you will work out that the Reynolds numbers for the velocities you'll be looking at will range somewhere from up to 500,000 now and beyond. But these Reynolds numbers are not the same as flow in a channel, where you base the Reynolds number on the entire the characteristic length, which is used in the Reynolds number, is the entire width of the channel. Here we're using the distance in x, so therefore we have much larger Reynolds numbers, and the transition between laminar and turbulence is taken typically on a perfectly arranged plate. The critical transition number is typically taken as 500,000. However, for the very short test plate that we've got, and if you look into the manual of the AF106 flat plate experiment, you will see that the manual states that the transition can occur anywhere between 100,000 and 500,000. Okay, so depending on whether we understand the transition occurring at 100,000 or the transition occurring at 500,000, we can look at the critical transition location. Okay, this in meters here, so at 100 mil, 200 mil, 300 mil, and so on, and you can see that the transition point is much lower with a lower Reynolds number critical transition number than it is with a higher transition number. Now, according to classical theory and the Blasius solution, the thickness of the boundary layer in the laminar flow region can be determined from delta equals 4.91x divided by the square root of Rex. Okay, so that is the thickness of the flow in the laminar region. When the flows become turbulent, then there is a boundary layer thickness which is given by delta equals 0.382 times x divided by Rex to the 0.2. Okay, so this only gives us upper and boundary layer thicknesses depending on whether we think it's turbulent or laminar or turbulent. What it doesn't really tell us very much about is the transition point at which it occurs. So what I've plotted here in figure 8.3 is a laminar boundary layer according to equation 8.3, according to Blasius, and then a turbulent boundary layer thickness according to this empirical equation here. And what we don't know is whether we go through a period of laminar up to, say, 0.05 meters, and then that transitions to turbulent, or whether the turbulence transition occurs later on. But what we have here is a region of uncertainty which depends very much upon external flow, how well developed the flow is at the inlet, whether or not the leading edge of the plate is really at that point there. So if it's there are a lot of reasons why what you're going to see in your experiment is going to depart quite a bit from this modeling. Okay. So one last thing to consider here. So what we're doing, we're going to model a square two-dimensional section with the inlet of 0.15 meters, height of the inlet 0.15 meters, and we're going to look at a domain length of 0.5 meters. As you can see here, this departs a lot from the reality, from the idealized flow of a flat plate, in which there would be no upper wall, but of course, because we are contained within the test chamber, we have contained an internal flow within the test chamber. This is obviously going to affect our results. In terms of the medium, the fluid medium, we're going to take it to be air, and the density of air at 1.223 kilograms per cubic meter, and the viscosity at 1.78 times 10 to the minus 5 kilograms per meter second. Okay, right, so let's start with the ANSYS Workbench. Bring up your ANSYS Workbench. And the first thing we're going to do is double click on the FLUENT. This keeps our FLUENT analysis. And just so we are clear that we are going to start with the laminar BL6 simulation of AF106, and we're going to use U equals 1 meter per second there. We can call that. Double click on the geometry, and the first thing to do when the geometry comes up is we're going to check our units. So we're going to work in meters there. So let's go up and have a look at units. Yeah, meters. Let's align it to the z-axis, and on the xy plane there, select the xy plane and create a sketch. On that sketch we're going to create a rectangle, and we'll center it on 0, and let's not make it too big there, like that. Okay, so now what we're going to do is get some dimensions on this. So we're going to get the vertical dimension, so select the first and the top and the bottom and this dimension there. So for this, for the height, we're going to call it 0.15, and then before we put the actual dimension in, let's get the other dimension coming off it like that, the horizontal one. Right, so we're saying that in the x direction we're going to have 0.5 meters, 0.5, and then in the y direction we're going to have 0.15, which is the distance from the plate to the top of the test section. Go back into modeling there, okay, and what we're going to do is create surfaces from sketches like that, apply, generate, and we can see it's created a rectangular test section there. We can zoom into that test section, and what it's created is a surface body. Now if you click on the surface body and then you go down to fluid solid, we can create fluid there. Alright, it doesn't need regeneration. That is all that is required from this, is a rectangular geometry. This is going to be our inlet on the left, that's going to be our outlet there, and this is our flat plate on the bottom, and that's the top wall of the test section on the top. Close down your geometry. Okay, double click and open the mesh. Now we're going to work on the meshing. So we'll wait. Here we are. Here comes up the meshing. So the first thing we're going to do, once this is finished importing the geometry, is to decide on how we're going to mesh up this entire problem. So you see that the surface geometries come in. Let's align it to the z-axis, so we're looking at the xy plane. Alright, and if you right click on mesh and then insert method, select that surface there, and what we're going to do is select the method on that to be sorry, delete that, I got that wrong. Insert map face meshing. Select that. So that's a map face. Okay. So if we go on to mesh, and you might want to check the size set on curvature, sizing on curvature. That's fine. So we can actually just generate a mesh straight away there. Let's have a look at it. Very coarse 1, 2, 3, 4, 5, 6 by 1, 2. A very coarse mesh. Right. So what we're going to do is refine this mesh. So we're going to insert a sizing, and we're going to go up here, select the tool for the selection of sides. So we'll pick up the top one and the bottom one there, apply, and on this we're going to have number of divisions. So if we go ahead and call that 50, we're going to have 50 divisions in that direction. Then we're going to have the same thing, but we're going to select the left side first, the inlet there, and we're going to have a number of divisions, and here we're going to put in 120. Hard behavior, and the bias we will choose so that it extends from small in this location to small in this location, with some big ones in the middle, and we'll use a bias factor of 1.2. So we repeat the same again for the outlet boundary, So we can just select the edge there. So we'll go number of divisions, 120, call it hard, behavior, and then we'll have small to large with a bias factor 1.2. Go ahead and generate that mesh. What we see now is a much more refined also on the edge sizing here for the top and the bottom, make sure you use hard with no bias. Okay, so if we look at that, we have equal divisions down the test section. We might want to play around a little bit with this, so we could actually make this 1.5 and this one 1.5. So there's what we'll see is it will refine it more and more in this area here. So you can actually change both of those at the same time. So we can zoom out, have a look at that mesh, like so. Okay. You can actually really change these if you want to by having a bias factor of 70. All right, now you can really see the distribution of the elements changing. That makes the elements very fine in the near wall area, and that gives you almost this black band, which is very fine meshes close to the wall, which is important for when you're trying to capture the boundary layer development in that area. So what do we need to do next? Well, we need to create some name sections for Fluent to know where the inlet and outlet are. So with that in mind, we can select the boundary, so in green now. If you right click on that, you can create a name section, and here we can call it inlet. All right, let's create a name section called inlet there, and now we'll do the same. We'll select this downstream boundary and create a name section called outlet. There we are. So we've got inlet, outlet. We don't need to define the walls. Okay, so those boundary conditions, as I've mentioned before in the other tutorials, U equals V equals 0, or the no slip boundary condition is set by default on boundaries which you do not define. That's all we need to do in meshing for the time being. What you can see is if you go to mesh and you scroll down on the details, on the statistics, it'll tell you that you've got 6,000 elements. Okay, so to match this with what we're doing in the actual tutorial itself, what we're going to do is increase the divisions on the edge sizings 2 and 3 to be 150. Okay, so that's just changed the mesh, made it slightly finer, and what you see now, we've got 7,500 elements. These are all quadrilateral, and we can close down meshing then and move on to the next part of the analysis. Now at this stage, because we made various changes, we've got a lightning bolt, you can see here, so you go ahead and you can just update that so that you'll have a green tick, which means that it's ready to move on to the solution stage. Right, so moving on to the next stage now, which is the setup. We can double click on that. The usual window opens for Fluent, asking us whether we want double or single precision. Just click OK to that, and we'll go straight into the analysis in Fluent. So just as a reminder, we'll double check that. There looks like the right mesh. So what we've got is the blue for the inlet, the red for the outlet. This rather fine mesh in the interior domain. So that's to remember what it was we were trying to model. So we're modeling the test section above the plate. We've got the inlet here, which is actually really half of the test section. It's where the flow comes over the top of the plate. We're going to apply a velocity boundary condition there, horizontal, U equals 10 to 30 meters per second, with a vertical 0. and we're going to put zero pressure there, and we're going to have an outlet boundary condition here, which will either be either outlet pressure equals 0 or a mass flow. So those are two different types of boundary conditions that can be used. And we are going to apply a turbulence for the turbulence modeling later on, so those boundary conditions are still retained there in the description. Along the top part of the test section, and obviously along the bottom plate, we're going to have the no slip, U equals V equals 0, and that will lead to this development of a boundary layer, which would hopefully look a bit like that. Right. So let's have a look what came in with FLUENT. So we've got the first thing we need to look at is the models, and we can see that the default viscous laminar model has been selected there. For the materials, also the default air has been used, which if you look at the values, we have 1.225 and 1.7894 times e to the minus 5 there. They're fine, we don't need to change those, not make a big difference. Boundary conditions, we've got an inlet, the blue one identified here. We've got a red boundary at the outside. We've got the interior surface body, which is all this green mesh. So let's have a look at the inlet. It's recognized as a velocity inlet, but what we have to do is set the boundary condition here. So for laminar flow, this first we're going to do 1 meter per second. Okay, nothing to do there. Outlet, it's recognizing a pressure outlet, but what we're going to do is we're going to change that, okay, just for the time being, to be outflow. Yeah, that's fine, and just leave the default. So that's another boundary condition used. You could use a pressure 0, but because of the very short nature of this domain, we don't really know how well specifying a 0 pressure on the outlet will behave, because we're still getting the flow developing through the section. That is really as much as you need to do for this first in terms of the analysis. We needed to check those the materials, which we've done. Then it's the laminar flow model. Okay, the boundary conditions, we've set the x velocity to 1. So let's have a look at that inlet again. So okay, so you can specify the components. So you could have, for example, we want to have the x velocity to 1 and the y velocity is 0. And that is the equivalent of having magnitude and direction specified. By all means, go ahead and do that, so that it's the same. Outflow, we've got the boundary conditions here, the inlet and the wall surfaces, which are these white ones here, the top and the bottom. They will be the wall condition, which is the no slip boundary condition. So let's initialize it. So the first thing, now we go on to the solution. There's nothing needed to be changed there. What we're going to initialize is with the hybrid initialization there, and you see that happens very quickly. And we're going to run the solution. So if I think we have suggested here 1,000 iterations. So let's put in 1,000 iterations here, and we're ready to run FLUENT now. So if we hit calculate, one thing to notice now is it's plotting up residuals here, scaled. They call them the scaled residuals. What you have in a laminar flow is you've a two-dimensional case. You have one equation for the set of equations being solved for the continuity, and two sets of equations for the momentum, the x velocity and the y velocity. If we had a three-dimensional laminar flow, like we did in the tutorial number 4, for the 3D flow in a laminar flow in a pipe, then you have one continuity and 3 momentum, so therefore you have 4 sets of residuals. Okay. Later on, we'll see that if you run a turbulence model, that you actually have that you add 2 transport equations, one for the K equation and one for the epsilon equation. So for a 2D turbulent analysis, you would be looking at residuals. 1 for the continuity, 3 for the momentum, for the 3 dimensions of the momentum, and 2 for each of the transport. So a total of 6 equations. If you are solving for a 2-dimensional turbulent problem, then you have 1 equation set of residual for the continuity, 2 momentum equations, x and y, for the momentum equations of the Navier-Stokes, and then you have the 2 transport equations, k and epsilon, so a total of 5 equations to solve. And here what we've seen is we've solved for 1 continuity and the x and the y. That's fine, that's closed. We can close that down now, and it saves the results. Okay, and there we see now that in our Fluent analysis we've got all ticks, and it's just a matter of looking at the results. Now we're not going to look at the results directly here. What we're going to do is to actually link the results to a into a standalone version of the results. So if you click on that one and you drop it there like that, what we can do is we left click on solution and we drop it onto results. That means our results are now transferred from our analysis here into this post-processing results section. So go ahead and double click on that, open up the results there, and this will take us into the CFD Postprocessor. So there we are, CFD Postprocessor has opened up, and this is what we get in the first instance. So just a quick note about the CFD Postprocessor. It's mainly designed for looking at 3-dimensional fluid flow. So when it does get a 2-dimensional flow, like we've just done in Fluent, it actually extrudes it slightly in the Z direction. So therefore you do have this additional sort of extruded surface. If you align that to the Z-axis and you have the looking down onto the YX plane like that, we can see that we've got the inlet, the outlet, and these 2 symmetry faces, and then the wall bodies on the top. Okay, so right, in the usual way, what we can do is we can insert a contour. So if we're going to look at, for example, contour 1 there, we just want interested to look at the pressure. Let's do it on the symmetry 1 plane. So you can see you've got these peaks of high pressure here, and then it's kind of a steady state down the line. You can look at the velocity as well. There. You may see some changes between what you're finding in the manual and what you're seeing here. But the velocities are roughly equivalent, and we do have that. You can see the boundary layer forming along the bottom plate here, and then of course you've also got a boundary layer forming on the top part of the test section. Just having a think about this now. So now we can also look at obviously vectors as well. So let's create a vector instance there, and there we are, like so. You can also zoom and look at the vectors like so. You can disable the contours. You can change the size of the symbol if this makes it more coherent, easier to look at in certain parts. You can normalize these as well. That doesn't really show you the development of the boundary layer. So now what we're going to do now is create a series of lines within the postprocessor here, which we're going to use to create comparisons. First thing we're going to do is create a point, and we're going to put the point in the middle of the inlet. So insert point. Okay, so now we know that the location at the middle of the inlet, so what we're going to do is create it at x equals 0, y equals 0.075, which is about halfway up here, and of course z equals 0. So if we do that, we see the point has been created right there. Okay, so now what we're going to do is create a line roughly at 40 millimeters along the bottom there. So insert location line. Okay, so line 1 we will call tap x at 40 millimeters there. And what we're going to do is we're going to say the line's going to go is going to be at 40 millimeters, which is right 0.04, and then it's going to go from 0 to the top of the domain on the y direction, which is 0.15, which corresponds to the top boundary, and we're going to sample at 200 points. So that's our 40. That's where our first foil is on the bottom. So you can do that, and you can actually just duplicate that first line, and we'll name it, the second one will be at 90 there, and don't forget to modify it. So this is 90 millimeters, so change that, and that will create our line at 90 millimeters. Let's duplicate that again, and this one we will create at 150 millimeters, and don't forget to change that so that we have it at 150 millimeters along the x direction there. And let's make another copy. So you'll notice that all of these coincide with the foil locations in the experiment. So the 220, we need to change that. There. So we've got 90, 40, 90, 150, 220, and we're going to create one last one here. Duplicate that, and this is going to be at 300, which is the last foil, and we modify it. So 300 is 0.3 meters, like that, and that should locate one right there. Okay, good. It might be worth having one at the outlet as well. So go ahead and copy that, and we can just say outlet. And the outlet is at 0.5. That creates one of the outlet. Okay. Right. So that should sort of match what you're seeing in your workbook. So now comes the slightly more complex task. You'll see that at the top here, we've got outline, a tab called variables, a tab called expressions, calculators, and turbo. So what we're going to do is we're going to use, first of all, an expression, and we're going to create our U infinity. So go right click, click new, call it U inf there. Okay, and in here you can type probe, capital V, velocity U at 0.1. Oops. Sorry, you need a capital there. So if that's worked out properly, if you click the apply, that should tell you 1 meter per second. So that's what it's getting, is from this point that we drew on here, it's pulling out the velocity at that point, which is the velocity in it that we told it, which is 1 meter per second. So we now have an expression, uinf, which has been created here, which gives us the velocity of the inlet. We could have set it higher, we could have changed it. So what we're going to do next is we're going to do the same, but we're going to create another expression called unormalized. So new, unormalized there, like so, right? And for this one, we're going to use, this should be velocity, and this uses the entire velocity variable, divided by uinf, the value of the expression we created there, and it should say it's created a variable there called unormalized. So now we need to go to the variables tab, okay? And here what we're going to do is create a new variable called unormalized as well, there. And for this, we're going to use the unormalized variable expression, calculated everywhere. So now we've got this. Okay. Let's repeat that again. Create new expression, and for this time now we're going to normalize. So y normalized there, and here we're going to have capital Y divided by 0.15 there. It creates a variable. Okay, you're still putting units in as meters. We go to the variables tab, and now we're going to create a variable itself called Y normalized there, and here we're going to use the expression that we just created for Y normalized there and apply it. Oops, I don't know why that happened. So why is that? No. Okay, so yeah, in that last step there, what we needed to do is, this expression is fine, so we create an expression called y normalized, which is y over 0.15. As our variable, we need to call it normalized y and not y normalized, because y normalized is already being used by the system. Okay, so if you create normalized y, then from that you select the expression y normalized and apply it. We now have this variable called normalized y. Okay, so we can plot. We can go back to our outline, and we could actually plot if we wanted to. In the contour, we can now plot those variables we've just created. So let's have a look at unormalized, and you can see, that we normalized our inlet velocity. We normalized our velocity everywhere, divided by our inlet velocity, which was 1, which gave us a non-dimensional u. And you can see that it's somewhere between 0 and 1. So it's obviously 0 along the wall, but then it's 1 everywhere else. Okay, let's create some graphs. So the first thing we need to do to create a graph is to go to Insert, and then down the bottom here you have Chart. Call it Chart 1. Okay, and what we're going to do here is we're going to use the first tap location, tap 40, okay, as on the data series. On the x-axis, we're going to use the velocity. You can have either velocity or normalized. Let's select velocity for now. On the y-axis, we're going to have y for now. So you click that, that'll give us a velocity profile at the first tap. Okay, so we can repeat this now by adding, going back to data series, we'll add the second one, a second series. Okay, so we may as well call this now already tap 90, and location tap 90, apply. Let's go back to that first series, call that tap 40, there, apply. So now you can see two different velocities, and you can keep on doing this then for tap 150, and the location tap 150, apply, create a new one, tap 220, location 220, apply, then tap 300, location 300, apply, and then let's do one last one for the outlet, which is at 500 mil, and we'll do that tap of the outlet. There we are. So we can create a title here. We'll call it velocity distributions along the plate there, and this is in meters per second. Let's differentiate later on, so let's try that, and there you can see it. So what we can do is obviously we can let's change the x-axis, because let's zoom in on what's happening close to these velocities. So let's say that we're going to go from 0.6 to just over 1.1, for example. We can probably make that slightly larger again. Right, so the first thing to clearly see here is that we do not have a classical laminar flow parabolic profile in the center. So there's obviously a development of the flow going on, which is probably quite unwelcome, but it's a consequence of the boundary condition that we've used, 1 meter per second. So it is progressing, and it probably will eventually find a parabolic profile if you kept on going. You can see this overshoot, which is quite high, past the 1 meter per second there, but what we're most interested here is if we look at this in terms of up to the half section, could we, let's limit the y range then to going from 0 to the midpoint, which we know is 0.075 there. So now we're only looking at the midpoint. This is starting to look a bit more like the boundary layer velocity profiles you're used to. What we haven't plotted on here is the Blasius solution, but then we would need a normalized velocity. So let's see. Now, luckily, the normalized velocity here is identical to the because our bound is 1. Our velocity in the inlet is 1. So what we have got is a slight development in. So if we were to take a line along here at 99%, so we've got 0.9, 1, 2, 3, 4, and 5, 9.6, 9.7, 9.8, 9.9. So that intersection of a vertical line there indicates, so it gives us the height at which 99% of the boundary layer has been met, And you can see that in this region here, we are looking at roughly up to about 10 millimeters. So that's 10 millimeters there. So we go 2, 4, 6, 8. So most of the boundary layer thickness there is between 2 and about 6 millimeters. Okay, so what we can do, we've got the velocity profiles along the wall there. We can actually export these. So you can export there, and what it does is it takes all your data on the graph. Now before we do that, we could normalize this, so we could actually look at on the x-axis we could use U normalized, and of course you can see it makes no difference because at this point you've got a velocity at the end of 1, but later on when we come to change that to higher velocities, you're going to have to scale it by that inlet velocity, so it's good practice. We can export this now anyway, like this, to a CSV file. I like to put that in my somewhere where I'm going to be able to locate it. So on my desktop, for example, we could call this laminar data fluent 1 meter per second .csv there. Save that, and if we go to the desktop, which is an absolute mess, well, we should see it somewhere here. Good luck. I have to export it again because I can't even find it now. Export, so it's still put it under music. Try again. This time get the right location. So there it is there. If we double open it, this is what it looks like when it comes out straight out of FLUENT Postprocessor. So what have we got? If we select all of it, change the number format, I prefer this anyway, go to number, and let's say 4 decimal places. So what we've got here is the U normalized value, which we've said that if the it was 99% of the free stream velocity, that is the location of the boundary layer thickness. So somewhere between 0.92 and 1.01, we've got a transition. So let's take the average of the 2 points just before it transitions. So we've got our boundary layer thickness is roughly 0.0026 meters, which is 2.6 millimeters. Okay, so we can do the same. If we scroll down the page, we can see the next tap location comes out there, and we can paste that equation there, which takes the average of these 2 points. So our boundary layer thickness is in 3.4 mil. And we scroll down to the next tap location at 150. We've got a transition between 96% and 100%, so we paste it there. We take the average of those two values and come down again, and let's do between 98 and there. So or we just type it out again, doesn't matter, it's easy enough. There. So now we've got the 220 tap location, which is down here. We see the transition between 97 and 100% there. 4.9 mil. That was the 300 mil. So at 500 mil, we've got transition between 98 there. So select all those individual values. Create a new sheet, paste, collect all the separate values. Right, I think we've got a bit of a problem there, so we'll have to go back to the model, and it is with the tap location 300, 0.3, 0.22. So we know that was 40, 90, 150, 220, 300, and 500. I have a feeling we have something from with our 300 location. I'm not sure what's wrong with that. Seems to have output it incorrectly. So if we just you can look at that. There is a problem with the 300, and I'm not sure why, because there isn't in here. Tap 40, tap 90, tap 150, tap 220, tap 300, and the outlet. Okay, so that was the end of the first part, where we have created a FLUENT solution for the laminar flow case. And we're now going to move on to the second part of this, where we're going to use exactly the same velocity of 1 meter per second, but we're going to use a turbulent flow model. Right, so the first thing that you're going to do is copy an instance of this laminar flow case here, and we're going to create a second analysis, which is a duplicate. So if you left click on the button and hit duplicate, so FLUENT will now copy the entire, so ANSYS will now copy an entire copy of this model A. And this one we're going to call turbulent boundary layer simulation of the AF106, the boundary layer experiment. So you can relocate this anywhere you want. Let's put it side by side like that. Okay, and what we're going to do now is we're going to modify the the model that's run in Fluent so that it is turbulent. Everything else remaining the same. We will use exactly the same mesh. So if you double click on Setup to enter Fluent, keep the double precision option. This will bring up the Fluent client. Okay, so you've seen this before in our tutorials 4 and 5. Let's maximize the screen. See, that's the same mesh we use in the laminar flow. We've got the blue inlet boundary there and the right red colored outlet there. Keeping everything the same, but now we're going to go to models, and you can see that by default it's got the laminar model that we used before. Go ahead and double click on that. And what we're going to use for this is the standard K epsilon model there, and we're going to use exactly the same options on the K epsilon model, so don't change anything. Just click OK. That enables our turbulence model. But now what we have to do is that we have to go and double check that the boundary conditions, so we go down to boundary conditions, go to inlet, then we go edit, and it brings it up, and you can see we're going to use exactly the same boundary conditions. So naught, pressure, keep it the same. We're going to have a y velocity of 0 and an x velocity of 1. Keep those the same. But right now, you note we have got a intensity and viscosity ratio, which is another way of defining this. We could potentially use, as we have done before, we can change this. We could have intensity and hydraulic diameter. For the time being, let's just keep that at intensity and viscosity ratio and click OK. So we can look at the outlet, and we can see that we're using the mass flow is exactly the same as the laminar one. So, okay, now all we have to do is run the analysis. So, as usual, we go to solution initialization, use the hybrid, we'll initialize that, okay, and then we go run. And with this one, what we're going to do is we're going to use 2,000 iterations, which will hopefully take us through the convergence. Yeah, okay, and we'll hit calculate. And let's see how we do. So you can see the residual stresses are now, the residuals are being plotted there as we go along. And you can see that for this case, as we talked about in tutorial 5, we've got one continuity, one set of scale residuals for the continuity. We've got two momentum equations to be solved, the x velocity and the y velocity, because it's a two-dimensional problem. And then in addition, we've got the k and the epsilon for the turbulence model, so the turbulence kinetic energy k and the eddy diffusion diffusivity epsilon, which solve two additional equations. So altogether we have 5 sets of equations being solved. And we can see it's converged there, so our analysis is ready. We're ready to go to the post-processing. So if you close down Fluent, there we are, that's done. So now we go back to our workbench. Now what we're going to do is, because we're going to compare these models side by side, right, is we're going to take the results from Fluent, from this solution box, and we're going to drag and transfer them over to a post-processor where they can, in combination, be shown together. Okay, so now if we go to the box C and double click, and we bring up the post-processor, okay, this is what we'll see. And you can see on the outline tree that we've now got a laminar case, yeah, and then also the turbulent case. So there's results from both of them. We can go ahead, and if you look at this window here, we can plot them side by side. And you can see the turbulent ones come in, nothing being plotted there. So we can align that. Now, everything that you've done for the laminar solution is valid for the turbulent. Now, at the moment, these windows aren't synchronized, but what we can do is we can actually synchronize the camera views. So that means that if we want to look at this, it'll now move both windows the same, so we can zoom in, zoom out. Now, let's have a look at some of these contours. You can see on the laminar solution the development of your boundary layer. This is the normalized variable that we set up earlier, and you can see that the thickness of the boundary layer here, when it's using the laminar model, is smaller, and the thickness of the boundary layer here, when using the turbulent model, is thicker. And that is consistent with what we would expect. Okay, so the lines, the locations of the lines that you created earlier on are all valid, and the points, everything is valid on both the models. So, and this is particularly the case because of the mesh. So you can see there that the vectors you can also that you created to plot and the contours are all valid one for the other, and this shows you the thickness of the boundary layer. You can see the velocity vectors at the outlet, and that's fine. So we can look at velocity vectors. If we disable the contour plot there like that, and let's have a look at the velocity vectors. And if we disable the line locations there, you can see the vectors plotted at mesh points. At the moment, these are normalized, or they're small. We can increase these, see a bit more difference there. So let's have a zoom in on some of these velocity vectors there, like that. Now, if we go down to, now let's have a look at the chart, see what we've got. And on the chart now, we have also got the plot in the same location, so you can see that for the laminar, which are the solid lines there, and you can see the turbulent, which are the dashed lines at various locations there. And you can see how generally the turbulent boundary is the velocity, and we're looking at this is the absolute velocity. Remember, we have the absolute velocity is in meters per second, but our inlet velocity was 1 meter per second. So if we were to normalize, we would have exactly the same magnitude value there. And if we were to draw, there's 0.95, 96, 97, 98, 0.99. If we were to draw a line straight up through here, that would give us the range of boundary layer thicknesses. And as you can see, we've got quite a wide range going from 2 mil all the way up to 10 mil. Okay, so you can also see that as we go down from the first tap location down to the last tap location, if we were to disable some of these here, you can extract them from the plots. Let's just concentrate. First of all, let's compare the two models at the last tap location. There. So we can see the boundary layer solution for the laminar flow in the dark pink. We can see series 6 here is actually let's disable that as well for the time being, sorry, like that. So let's just compare at the final line, so you can see significant differences there between the turbulent boundary layer and the laminar boundary layer. You get this overshoot of the velocity that wants to come back then. So it's not, first of all, it's not a fully developed flow. And this is something that you will find in your experiment anyway. At 0.9, so you can see if you would pull the 0.99, which is representative for the boundary layer, the transition to the boundary layer point, you would have roughly about 0.45 mil, 4.5 millimeters or 0.0045 for the laminar, and you would have, pull it up here, so we'd have roughly 6, 7, 8, 0.8, so it's about 8 mil. So that's pretty consistent with what you would expect. So I think the simulation has been quite successful. Now you can export all of these series here into by clicking the export button, and that will export the entire. So if we go tutorial 8 lam 1 millisecond lam versus turb at 1 meter per second there. We can save that, right, and then we can open it up in Excel. So this will only output what's on the, when you export, it will only output what you're actually seeing on the chart. Okay, so we take the X direction. So the second one we're plotting is the turbulent solution, and this is output at the 220 mil tap point. There. So we can see that we've plotted the laminar versus the turbulent there. And this is straight from the CSV file that we exported. Now remember that we're only really interested in the lower half, and so half of our width of our, so from the boundary layer plate up to the top of the test section is at 0.075, so we can limit our y-axis there, so we're only interested in those. Let's change the number there, and let's just plot that to 1.1, and then take the lower limit as 0.8. Alright, so the first series was our laminar flow solution. So we'll go up here just to double check that. So tap 220 for case boundary layer laminar flow solution there. And our second one was the turbulence. That gives you two different results, one for the turbulent, one for the laminar. So we can edit that. Laminar solution, and we'll call series 2 turbulent solution there. Okay, and so now again, the way to if we change the number of divisions here, so we call the major unit 0.01 and do that. That's maybe too small, too big. Sorry. Okay, not quite as trying to get this so you can actually see the so 0.99, which is where the boundary layer is where the transition between the full stream velocity. So at the point 0.99, which would come up here, you can see that the laminar solution, would correspond to just under 0.01. So what we need to do is plot maybe some grid lines that will show it clearer. Primary vertical, major there, grid lines, primary vertical, minor. So let's do 0.02 and fix 0.01. So that gives us, so this point here, and then also we're going to have to do this as fixed 0. There, and then we're going to do grid lines across the horizontal as well, minor and major. So just to double check, what we were plotting here was our y value, so we can actually even reduce this so that we've got the same graph as on the so take it as 0.02, 0.02 there, and then we got 0.99. So our crossover point here is roughly she gives you the mesh point. So there we are, probably at just here, so 0.01. What we do need to have is probably change the scale on this so we can see what we're doing. And then we want to change the number format. Okay, so here we are. These are in millimeters: 1 millimeter, 2 millimeter, 3 millimeters, 4 millimeters, 5 millimeters. So at 0.99, which is transition, we're roughly here, which takes us to 0.46 maybe, so 4.6 millimeters. And then for the turbulent, we're actually just above 0.08, which is 8 millimeters. So for that 1 meter per second, we've got two different values of roughly about 4.3. That's one way to extract the boundary layer thickness at the 220 mil point. You'd have to repeat that for the other locations as well. So we can save that there as an Excel workbook this time. There we are. Right. That is how we would sort of post-process the results, get them and export them. There's more explanation in the tutorial about how exactly we find the 99% line, and then you can then import those values and plot them one against the empirical values there. So unsurprisingly, we actually get quite close, good results. Okay, so at this point, really, it's over to you. So what I would suggest that you do is now go back to your workbench here, save it, right? And once it's saved, I would make a copy of this, and what you're going to do is just simply change the velocities. So you're going to have turbulent bound linear simulation of AS at u equals, say, 20, for example, there. Move that to there. And repeat that now, so that you could have a copy of that. At 25, like that. And then you can have a final one now at 30 meters per second. Like that. Okay? So in each of these, you go in, you change the velocity to 20 meters per second, and you run it. Okay? And what we're going to do is get rid of that. So we just copied the results as well. So what we're going to do is move this down to there. And when you've got results, you're going to drop them in here. And now you're going to compare all three of them in exactly the same way. Okay? And that is really the point where it's up to you to play with. Okay? So hope you've enjoyed your tutorial number 8. And I look forward to talking to you soon.